There are other methods that you can transform the alcohol into alkyl halides. For instance, you can treat the alcohol with HCl, hydrogen chloride, hydrogen bromide, hydrogen iodide. Simplest method, very old school, primitive. But this works best only with tertiary alcohol, and I will tell you the reason behind it. Primary and secondary alcohol, they tend to react quite slowly, and you need very harsh condition like high temperature. So this is the reaction pathway. You can see alcohol, you put HX to it, you replace the OH with the X, byproduct H2O. Very clean, very green. And we know that the reactivity is best for tertiary. So how do we do in the lab? We will put pure HCl HBr gas into cold ether solution of alcohol. Ether is a solvent. You have a COC group, COC. Let me draw for you here. Not Clash of Clans, okay? COC. Yep. This is ether functional group. Ether is a good solvent. It's polar, but yet it's organic, so dissolve many of the organic compounds that you find in the lab. At 0 degrees Celsius, you see a substitution going on. To convert primary or secondary alcohol into the alkyl halide, we prefer to use thionyl chloride, symbol SOCl2, or phosphorus tribromide PCl3. Because this reaction takes place readily under mild condition, sometimes RTP or just a bit of heat, warm. The reactions are less acidic and also less likely to cause an acid catalyzed rearrangement that you get byproducts which you want to avoid. So this is a schematic diagram. Benzoin, throw in some SOCl2 in the presence of a base, pyridine. You can also act as a solvent. You get the chloride product. SO2 and HCl, they are pretty harmful. They are acidic gases. It will choke us, causing some respiratory problems in human beings. So that's the reason why we also use pyridine, which is a base, to absorb the gases. You get an acid-base reaction, so the gas won't come out and go to our lungs. Here in the last scheme, butane 2-ol is being converted into bromobutane. Very good, you. Let me introduce to you something called the Grignard Reagent. If you study chemistry at college level or in the university right now, you have to learn what is a Grignard Reagent. Organic chemists have to know this. So it is named after the discoverer, Victor Grignard from France. Basically, what he discovered was it is like an alkyl magnesium halide. So in short, it is in the form of RMgX, where R is the alkyl group, Mg magnesium, X a halogen. It is a kind of organomagnetic compounds because they contain a carbon metal bond. Now recall that, right, in a CX bond, in the ordinary carbon halogen bond, this is polarized. The carbon is delta plus, the X is delta minus. But now you throw in a magnesium. In this case, magnesium is the most electropositive because it is least electronegative. So Mg here is the one that prefers to lose all the electrons. It doesn't like any of them. So what happens is you throw Mg to it, Mg becomes 2 plus, and then the R, which contains the carbon, takes the negative charge. Remember in the previous lectures or slides we talked about electronegativity? Who's the boss? If fluorine is there, fluorine must take the electron. Fluorine always takes -1 as its oxidation state. In this case, Mg must be taking a +2 oxidation state. So I must be -1, and this carbon after the addition of Mg must be -1 as well. You need to do this in the presence of a ether, so you can use ether or THF, tetrahydrofuran. The structure looks like this. Pretty cute. Looks like a human. Once you form a Grignard reagent here, for instance, this is a methyl magnesium iodide, this carbon becomes basic and nucleophilic because the lone pair over here is able to do a lot of attack. Right? So Grignard reagents react with weak acid such as water, alcohol. You know, they are not even acid, but we call them weak acid because they still have the ability to give off H+. Carboxylic acids, even amine, they will abstract the proton from them and give hydrocarbons. So now if you throw in this halogen alkane called 1-bromohexane, put some Mg ether, warm it up, you get the Grignard reagent, throw water inside or just give some moisture to it, or blow, you get hexane, hydrocarbon. Very wasteful because you're trying to form alkane. You don't want to make alkane in the lab. Alkanes are supposed to be extracted from crude oil. So these are carbon-based nucleophiles in many laboratory reactions. Now in alkyl halide, because we know that the bond is polarized and the carbon is electrophilic, so it attracts nucleophile. So alkyl halides undergo substitution at the carbon which is connected to X. Here you see a nucleophile called hydroxide. It like to attack, push electron towards this carbon that wants it, kick out the bromide, and tada, you get the alcohol. We call this a substitution product. Why substitution? One reagent, second reagent, you get one product, two products. So two reagents, two products, there's no change. Substitution, just in a game, right? Football game, netball game, hockey game, you do substitution, one for one exchanged. We call this a leaving group because the halide has left the original substrate and came out on its own. So in general, the template is this: Rx alkyl halide, you put in a nucleophile, you get R nucleophile with the X minus bond, the halide. If I put Rx with a neutral nucleophile, then you get R nu H X minus, and after that this X combined with this H, pick this up, the bond break goes back to the Nu, the two neutral products.